throughout social media platforms. I want to thank my co-organizers, some of which are here today, but Kit, Christina, Marat, and Krishna, and many of the colleagues and staff who help us promote this seminar. Today we have a very special guest, Monique, Dr. Monique McClain. I'm super excited to introduce you, Monique. A little side note is that I met Monique when she was a graduate student. I probably read a lot of her papers. I've actually read your pieces of your PhD thesis. And that was maybe a long time ago. And now Dr. McClain is an assistant professor at Purdue University since 2021. Before that, she was a research scientist working with Chris Villes at Oak Ridge National Labs and in the area of big area additive manufacturing. Before that, she received her PhD from the School of Aeronautics at Purdue University and a bachelor's degree from UC San Diego. Her main research interests are in the area of additive manufacturing of energetic materials. We will hear a lot about 3D printing and combustion of these materials today. I'm super excited about that. And she has received many awards, but most recently she received the Air Force Office of Science and Research Young Investigator Award. And we look forward to your talk today, Monique. Welcome.
Thank you very much for inviting me, and I'm happy to talk to you all today. So should I go ahead and share?
Yes, please.
Okay.
And then,
okay.
All right.
And then presentation.
Perfect.
And, let me swap. Is this
there
good?
You go. Perfect.
All right, awesome. And let me grab a laser pointer just in case. Okay, so thank you everyone for attending today. I'm happy to talk to you about how we additively manufacture composite energetic materials. So before I get started on kind of the nitty-gritty technical details here, I want to make sure everyone's on the same page of understanding what I mean when I talk about energetic materials. So energetic materials are used in many aspects of society. So it's something you may not think about necessarily in everyday life, but essentially they're materials that can be classified as like explosives, propellants, pyrotechnics, some fuels, but essentially they contain a lot of chemical energy that can be released. So of course we could use that for, rocket propulsion, for example. We could use it for a wonderful 4th of July fireworks show. It could be used to pressurize your airbag in your car to keep you safe. And there are many, many more applications of these things. However, energetic materials, even though they release a lot of energy, they tend to be pressure and temperature dependent, or they could be sensitive to humidity or other factors. So in general, it's really important to understand how they perform or how they respond to these different kind of external environmental conditions, because if we don't understand how they respond to those, we don't understand, will they give off the energy that they're supposed to? Will they be, can we operate them safe with, can we use them safely essentially or not? So in general, there's a lot of importance in understanding how these energetic materials perform. And again, they're used in many aspects of our society. So anywhere from the government to, commercial vehicles to all kinds of things use energetic materials. So even though energetics is a very, very, very broad category, I'm going to be focusing mostly on composite solid propellants today. And then towards the end of the presentation, give a little teaser about plastic bond explosives. But in general, energetic materials tend to have common features. So I'll be focusing mostly on composite solid propellants here. So to break down what's going on, composite propellants are essentially mixtures of polymer with a high particle content. So you can think typically it tends to be above 70 volume percent or above 85 weight percent, kind of depending on the types of particles that you use, but very, very high content in general. So typically we'll have, the particles will have will be an oxidizer. So some of them will look like large particles like this. So you'll have some coarse particles, you'll have some fine particles in between to help improve our packing ratio, but we'll have oxidizer, which tends to be ammonium perchlorate in the propellant. So that makes the majority of the particles, and they tend to look be like crystals. Essentially, they look a lot like sugar. And then we can include some other particulate additives. So for example, we could include some aluminum particles to help it burn faster, or we could include iron oxide as a catalyst. And there are plenty of other additives you could include in your mixture. Beyond that, like the polymer that holds everything together is typically some sort of viscous resin system. So a common binder that we use is called HTBB, or hydroxyl terminated polybutadiene. And it's a polymer that can be cross-linked thermally over time. So typically you mix it with some isocyanate, and then you put it in an oven at elevated temperature to help it cure within maybe a few days or up to a week, depending on what kind of ratio you have there. But in general, when we're making a propellant, it starts off like a slurry because we have all these particles in this polymer. And then over time, once it's in a mold and we thermally cure it, it's going to turn into kind of like a rubbery state. So I like to think of it like kind of like a pencil eraser type of consistency. When we work with these types of materials, in general, the particle content, so your solids loading or volume loading will increase the viscosity. Your coarse to fine ratio of your particles can also change that as well. If you include things like nano additives, that will obviously make it more viscous as well. So in general, these propellant slurries are very viscous. They also harden over time because of the isocyanate. So processing this material can be a challenge, especially if you want to make certain types of shapes. So now we're going to kind of back out into the bigger picture here. So first I was talking about what, are the ingredients of this propellant. But now I'm going to talk about, okay, overall, what do we care about in a solid rocket motor? So in general, our propellant, we want to form that into a particular type of shape because that is the main fuel of our solid rocket motor. And that shape of that propellant grain is essentially going to be burned over time. And the way it burns over time will affect the thrust that's generated from that motor. So for example, you could potentially design a shape where your propellant motor, so like if you have your thrust versus time, as that propellant's consumed, it could be accelerating over time. It could be, maybe not accelerating, or it could be decelerating. But the way that it burns over time is going to be very critical to whichever mission the motor has to accomplish. So whether it has to glide very far or go very fast. So in general, the way we design that fuel is going to be really important because how it burns is pressure dependent. Like, so the pressure of the chamber will matter. It will also depend on that initial geometry that we design. So how do we make those initial geometries? So typically we cast a material within a mold. So this wouldn't necessarily be a mold because we have a nozzle at the end, but imagine the nozzle is cut off here, and essentially we have a few options of what we can make. We could pour our slurry into basically a cylinder. We could potentially just have the whole thing filled up. And if we did that, and if we essentially ignited the motor so it burns from this end outward, what we would have is a constant burning surface area. So essentially, as the propellant regresses, that burning surface area is going to be the same because it's just a circular cross section the whole way. So this will give us a particular type of thrust profile. However, if you want to change that thrust profile from something like an end burner, essentially you would need to have different kind of internal geometries. So the way we can make this geometry is by having some mandrel in the center here and then pouring that slurry around it, letting it cure, and then we remove that mandrel later to get this internal geometry. So based off of that, we have several options. We could have a very simple circle here. And if we burn this, essentially we would ignite in the center, and then this burning surface area would increase over time, which would change how it burns, or the thrust profile. We could do fancier types of mandrels where we could have like fins or some weird grooves here. But as you can imagine, the more complicated this mandrel design is, the more challenging it's going to be to remove. And it's really important that when we design these propellants, that removal has to be done in a safe manner. So we don't want like this fin to break a part of our propellant. Because if it does that, then our propellant's going to burn in an uncontrolled manner. It's going to pressurize much faster than it should, and it could blow up the motor. So in general, we do have to pay attention to how we remove these fine features in here, right? So typically, like I said, we can use a physical mandrel to make some of these shapes, but that limits what we can remove. We could try to use chemically removable shapes, but then you have to think, okay, is there residue that's left over here, and that will that affect how it burns? And then of course, there's more complicated methods like machining your propellant grain directly, which, as you can imagine, may not be the safest option. And the worst case scenario is if someone has to crawl into a space shuttle booster and inspect, in person. So that would obviously not be very safe. So in general, what we want here is we want a way to increase the amount of geometric freedom we have in making our propellant grains. And we want to do that with good control. So we don't want to be constrained by a physical mandrel or machining process here. Okay, so naturally that led us to think, okay, maybe we could use additive manufacturing to do this, because at the time we started looking at this work, or starting this research, additive manufacturing started to become more commonly used in many different industries. And I'm sure, as many of you are aware, additive manufacturing means you build something layer by layer rather than, starting with stock material and removing it or casting that material, for example. So it's been used in many different industries to make more geometrically intricate parts. And it can also be used to make material gradients, which could be of high interest to us as well. So in general, we're thinking, how can we use 3D printing to change how we make energetic materials so that we have more flexibility on how we design a solid rocket motor, for example? So first, I'm going to talk about the 3D printing method we developed here at Purdue. So in order to do this, we developed a method here called vibration-assisted printing. And the reason we had to develop this method is based on commercially available 3D printing techniques, like direct inkwrite or fused filament fabrication or other types of methods. There were a lot of limitations with those, and they weren't really made for energetics. A key limitation with those is you have to have like a minimum volume loading or solid loading content of your particles. So for example, if you only had 50 weight% of your propellant particles like ammonium perchlorate in a binder, it's not really going to burn, or it's going to burn very poorly. So typically we want something above the 80 weight% range, so we get something to burn more decently and to have self-propagating combustion. So that requirement there kind of limits some of the methods we can use to start off with. Because you can't have high particle content in certain types of processes like fused filament fabrication, for example. That would be rather challenging to do. Another issue would be, okay, can we process this viscous mixture? So again, I was talking about how these slurries, the more particles you add, the finer the particles or whatnot, the harder it's going to be to, essentially extrude that material out. So commercial direct inkwrite was not really amenable to what we were trying to do. Especially at the resolutions we were looking for. So we decided, okay, well, let's try developing this new method, vibration-assisted printing. So basically, this part here is very similar to just normal direct inkwrite, where you have your material in a syringe. You have some way to push that out of a tiny nozzle, right? So we use compressed air, but you could use a motor plunger system, for example. But the key thing that we did that's different is at the tip here, we added an ultrasonic probe that applied vibrations at the tip of that nozzle. And what those vibrations did for us was it allowed us to deposit this material much faster. It could be a much more viscous material than when we just did direct inkwrite. And typically the nozzle exit diameter would be smaller than if it was just pure, direct inkwrite, where we just push the material out. So there are several advantages to this technique. So in our first paper on this technique, we were really showing, okay, what kind of viscous materials can we print with this, and how does this process work? So for example, we've printed a few different mixtures. So this would be like aluminum mixed in some sort of epoxy that we deposited or extruded. We printed things like clay, for example, And this is a little ship that's freestanding actually. So we could print materials that were like viscous enough or stiff enough to be freestanding. So the picture's misleading, but I promise if you flip to the side, you would see the mass standing upright. And then we printed some food mixtures. So things like fondant, cornstarch, and sugar mixtures together. So again, they're stiff enough to be freestanding. So this was kind of our initial work here on demonstrating this technology, but how does it actually work? So before I play this video, we're going to mostly focus on this right side here. So there's more details in the paper on this and the supplemental video. But in general, when we are applying vibrations, we're applying them at the tip here or near the tip. And we wanted to understand like how the flow will change. So essentially, when I play this video, first you're going to see that when there are no vibrations applied, this clay is going to barely move. It's going to be hard to see visibly to the eye. But as soon as we apply vibrations, you're going to see that it moves much faster. So I'm going to start playing it now. You can see it's barely coming out without vibrations, but it's way faster with the vibrations. And the reason for that is now we're looking at the nozzle walls and the material flowing out. We're shaking the nozzle in a way that this material is sliding out without experiencing the same amount of friction that it normally would without the vibrations. So as you can see, it allowed us to print these viscous mixtures at orders of magnitude faster at this very small nozzle diameter, which I think these were 600 micron nozzles, and I think the actual diameter was about 400 micron. So that was kind of the basis of this 3D printing technique. So we had this new promising technique. Okay, let's go print some solid propellants. So we went ahead and started doing that. So we printed 2 different types of mixtures. And really the important thing about the study was that we showed that we could print a traditional type of propellant mixture without including solvents that have to be evaporated out later or some other additives to make it more shear thinning than normal. So that was also an advantage of this paper. But essentially, we started with 85% salt loading of ammonium perchlorate. So there are no other fancy additives here. We do have quite a lot of fine particles included in here. And part of that is because our material, when we mixed it with the HBB, which is our traditional binder, it wasn't really stiff enough to retain its shape on its own if we had much less fine particles. So even though this is not ideal from a packing perspective of large to small particles, it did help us stiffen this mixture because otherwise it would kind of slump. And then we also reduced the size of the coarse particles. Usually this would be like 200 micron, for example. But in general, we were able to make some printable mixtures with the HGBB as the binder. So we have our mixture here and we measure the viscosity of that. So relatively viscous. And we measure that over time. And then we also made a separate mixture with UV curable epoxy. So again, still ammonium perchlorate. And then just the only thing that changed was the binder. And we did this because, you know, we saw that this HGBB definitely slumps a bit, which is not ideal. And we know it takes a long time to thermally cure. So we wanted to start exploring the concept of, can we use something that cures much faster? Because if you're trying to 3D print a complex structure, it's not to your benefit to have it deform while you 3D print it. But in both cases, we achieved relatively high volume loadings. And since then, we've been able to tweak other mixtures that can be higher than this. Okay, so yes, we could 3D print the propellant, which had reasonable surface finish, but that doesn't tell you anything about the quality of it. When we're 3D printing or manufacturing propellants in general, we don't want unwarranted voids or delamination occurring because, again, that propellant is just going to burn much faster than it should. So we, of course, wanted to see what our 3D printing process induced porosity. So what we did was we took some micro CT scans of several different propellants. So just to orient you here, these top 2 propellants had HGBB as the binder. These bottom 2 had that UV curable epoxy as the binder. These left 2 are cross sections of the 3D printed strands, and these right 2 are cross sections of the cast strands. So to note, like if we're burning a propellant, it would be burning, like the flame would be on this plane essentially. So what we did was first we were looking at these HGBB based propellants, and we saw that okay, there is porosity, so that's not ideal, but porosity is something that can happen in a normal manufacturing process. But what we did notice is that when we use the epoxy, especially for the 3D printed strand, we essentially had a pretty close to full density part. So what that kind of told us was that this porosity induced in this HBB was likely not due from the printing process. It was likely due from our HBB mixture. So in our mixture, we included some tepanol, which is a bonding agent that has been used for propellants before, but it's known to off-gas ammonia. And the way to kind of remove that porosity is to mix your propellant in vacuum for a very long time, like hours, to remove that. So that was not done in this case because these were small batches. So it's natural that there is some porosity here. But in general, if we compare, we don't really see that with these epoxy-based ones. And then also, if we compare like these cast samples to these printed samples, in both cases, the density improved in the printed samples. So the printing essentially kind of helped us improve some of our porosity issues in the HBB, but in general it was not the main cause of these defects that we saw. So once we, tested this microstructure, we did burn these propellants and we found that 3D printing did not negatively affect how they burned overall. So that was very promising for us. Here I just have like kind of a quick video of what that printing process looks like. So I'll orient you before I play it, but this here is the nozzle and it's depositing a rectangular path here, depositing the propellant. So you'll see that as vibrations are applied, material comes out and the vibrations stop and nothing comes out at that point. So you see it just kind of hangs out. And we can essentially do that again and again to make these types of propellants. But even though we demonstrated we could print propellants, the question is, what comes next? All right, so now we're going to dive deeper into photopolymers for propellants. So as I mentioned in the previous study, clearly HGBB, even though it's our traditional rocket binder, it is not going to be a sustainable option for 3D printing because everything's going to deform, even if you try to make your mixture stiffer. Photopolymers tend to cure much faster, and they're used commonly in other 3D printing processes, so it made more sense to look into that deeper. And we decided to try like new photopolymer mixtures because the one we used before had some issues with the vibrations. Sometimes it would clog the nozzle. So in general, we thought, okay, there's plenty of other mixtures to try out there. Let's go ahead and do that. So in general, when we're talking about our requirements for photopolymers and energetic materials, we need something where we can have a reasonable cure depth. So it would not be ideal if the cure depth of your propellant was less than your print layer, because then you would have regions of uncured propellants as you are printing, essentially. So it at least needs to hit that. And in general, our mixture has to be able to handle opaque additives, because in propellants, even though the majority of the particles are ammonium perchlorate, which are clear crystals essentially, you will have opaque additives like iron oxide or aluminum. So and the content of that could be around 15%, for example. So that does need to be accounted for here. So it has to cure reasonably deep within if there's some opaque additives. So what we did was we looked at trying to make a new commercial off-the-shelf mixture. So for our, we tested the photopolymer mixture first, and then we added 15% of that to like a mixture with, ammonium chlorate and aluminum. So we had 85% mixtures of that, but focusing on the photopolymer first, we picked VAPO as our photoinitiator because that's fairly common photoinitiator with a higher wavelength. And it was definitely not that toxic compared to other ones that are out there. We chose HDDA as our reactive diluent. And also we chose that because VAPO is slightly soluble in that, but there's certainly other options to choose from in terms of that. And then we chose a polybutadiene urethane acrylate as our oligomer. So the one we use happened to be fairly viscous. So it did cause some challenges in our study, but we are working on tuning this a bit more with some of my current grad students. But in general, we were able to kind of make this mixture by kind of heating it and sonifying the parts together so we could do some tests in the study. But first we looked at the photopolymer and then we added that to our mixture. So again, we varied the aluminum content of that. So we went from 0% aluminum all the way to 20% aluminum. We had 2 different wavelengths that we tried, and we tried some different UV intensities. But in general, the setup was relatively simple. What we did was we had some sort of uncured either photopolymer mixture or propellant mixture in our Petri dish. We had some light that we measured the power of applied over some area. So that's how we calculate our intensity. And we apply that on the surface of this uncured mixture. And essentially we would apply the light for a certain amount of time. And based off of that, we would then remove or turn off the light. Then we remove the uncured portion and measure the thickness of that after we cleaned it off. So in terms of measuring things from this experiment, we also used an IR camera applied to or looking at the surface. So we essentially measured the temperature change from this curing process and just kind of looking at the overall behavior. And we did that by, as soon as we saw some sort of light being applied to that Petri dish, that would count as time 0. And then we would also look at like the maximum temperature change from this relative temperature. So we'd look at, oh, okay, at some point, for example, this photopolymer reached really high temperature, but we calculated the change in temperature, right? So this is more like 110 degrees change in Celsius. But that's how we essentially measured some of these features. So we measured things like how much time it took to get to that max temperature, what that peak temperature was, and whatnot. So here I have some examples of that. So this is just of the photopolymer itself. So just to orient everyone, here was our kind of test matrix. So we had 2 different wavelengths or gooseneck lights that we could choose. Again, we measured the power of each of these lights. So we knew that. And then before we tested, we measured the area of that light. So with that, we can calculate this intensity value. So you can see that we have like 2 pretty low intensities and then 2 higher intensities. I'll highlight that. And then we also measured, okay, like what was that diameter growth rate? So we kind of looked at, okay, what was that final diameter? And then like how much time did we apply the light for, essentially, based off the IR image data. And then finally, here's some other data points. So how long did it take to reach that maximum temperature difference? So we could see for these higher intensity ones, it was relatively short, and for lower intensity, it took much longer. And then we calculated that maximum temperature change, essentially. So you could see that for the raw photopolymer, it could get pretty hot. However, when we did this for like the actual propellant mixtures, it was much lower temperature. So it wasn't actually a concern for us for energetics. It was not hot enough to make it ignite. So that was a good thing. But here I have some curves of our or like IR image camera curves. So here on the left, these are sample curves of the lower intensity UV curing. So these would be the unboxed conditions here. So we changed the time that the light was applied for, and we measure the temperature change over time. So we could see that in general, 15 seconds is not really that long in this case. It doesn't really reach kind of that asymptotic region that we see as we increase the time. And in general, we can see that the temperature maintains itself pretty well in the reaction. So there's not extreme cooling or anything going on there. However, when we use the high intensity conditions, we can see that it rapidly begins curing and increasing in temperature. And we could see that, okay, 15 seconds is probably long enough to get it to react. And then we can see that as we just leave the light on longer, all that's happening here, well, not all that's happening, but in general, it's starting to cool because it's so hot. But in general, when we applied the light, we kept the light on the entire time for these test conditions. But the main point here is that we're really trying to understand like which factors affected this photopolymer, and pretty much the intensity was what was important. And a quick note, like the intensity was a little hard to keep consistent because the area kind of changed a bit and the power was slightly different. So in the future studies, it'd probably be better to control this better, but in general, we can see that there are significant differences between the two. And then finally, we moved on to testing the actual propellant mixture. So now we actually looked at, okay, what happens when you have 85% of these particles? So you could either have some content of aluminum up to 20% or just all ammonium perchlorate. And then here, this is where we measured the cure depth of that propellant. So what we did was kind of the same type of study, but we were focused more on like the depth that it cured at. So what we found was in general at these lower intensity conditions, which are these guys down here, even though, you know, it's not going to maybe cure that well in terms of mechanical properties, it did cure deep enough for our printing process. So typically our layer heights are about 0.25 millimeters or 0.3 millimeters. But this is much larger than that. So even with low intensity light, we can cure relatively well. Of course, if you have higher intensity light, we can cure much deeper. So we can cure anywhere from about 1.6 millimeters to 3 millimeters. But in all cases, if we have aluminum in that, it's still going to cure deep enough in our particular printing application. So that was really promising for us. But in general, there's a lot more work to be done in understanding essentially what's going to happen with these cure depths, you know, because if you cure layer by layer, now you're going to have these interfaces between your print layers, and it's not necessarily going to be as strong as if you just had something completely cured altogether, like with traditional isocyanates and HBB. So there are definitely challenges with trying to figure out like how do we improve these mechanical properties. Also, just as a side, this is a sample that we micro-CT'd of 4 different cured layers. So there were no obvious issues here, but again, we have to do more mechanical testing. And this is just demonstrating that with the photopolymer, this propellant will still burn. But we still need to characterize the combustion properties of these photopolymers. So this here's kind of a teaser for what we're working on next. So we've essentially started tweaking the ratio of these ingredients because again, that oligomer is very, very viscous, and we probably had too much of a content of that HCDA mixed with that oligomer. So we've tried to improve that ratio. We're trying to do some tensile testing of some inert propellants. So here's an example of one of those here. And this is, you know, it's not necessarily a successful sample, but the point is to demonstrate here, you know, we have a dog bone type 1 specimen. It's 5 millimeters thick. So we cure from both sides. So we have 2 cure layers, but point being that, you know, obviously that cure layer is going to be pretty weak. So this is an example of how it got stuck and my students are trying to take it out. And then of course it started breaking at that interface where it was curing. So it's going to be really important to understand, are there ways to improve that adhesion between those 2 cured layers? Or do we have to explore something like dual cure mechanisms where we partially UV cure and then complete the cure thermally later? So these are things that my students are working on now. So they're looking at, you know, testing cast samples. They're looking at testing 3D printed samples as well. Okay, so next I'm going to get into multi-material 3D printing, essentially, of our propellants. So like I mentioned, we're interested in geometric, making new geometric patterns for our propellants because that controls how they burn. But why can't we control how they burn by changing the material content within the propellant grain itself? So the idea was, you know, can we print multiple types of propellants into one type of strand and see how that burns dynamically? So essentially we would 3D print 3 types of propellant mixtures here. So the outer layers are just normal ammonium perchlorate propellants, and the inner layer either has a bit of nano aluminum or a bit of iron oxide. So it should burn faster than the outer layers. And we have some images of what those look like. So for example, this here will be, the white is essentially the ammonium perchlorate propellant. So no additives there. And then the middle layer has a bit of iron oxide in it, which is why it's red. So when we printed these are about 1 millimeter thick layers. We can see there's a little bit of intermixing here between the layers, but considering overall that this is relatively thin, right? It's only about 3 millimeters thick. You know, this intermixing is not terribly bad for our first attempt. And honestly, I think it could improve if it was more viscous mixture, there would probably be less mixing at this interface. And then here I have an example of the other type of propellant mixture. So again, we still have ammonium perchlorate on the edges here, but then in the middle, we have that nano aluminum mixture. So Here, for example, that interface is much more defined, and that's probably because the nano-aluminum is stiffer. So that interface will probably be a little better. There won't be as much intermixing. But in general, we're printing relatively small scales here at multi-material parts. So in general, we're trying to understand how, kind of changing the propellant composition at small scales will affect how it burns, or maybe even mechanical properties. So I have a video for you showing how it burns. So I'm going to show a layered nano-aluminum propellant. And typically, if it was not layered, so let's say it's just ammonium perchlorate, what should happen when you burn it at high pressure is that it should ignite and then burn flat or linearly. But here you're going to see something different. So here we ignite it, and then over time, you'll see that there's some sort of burning surface area developing. So we develop this V shape that eventually becomes pretty stable at some point, right? It doesn't really increase anymore. So we really want to understand, okay, how long does it take from ignition to go to this V shape? What is the length of that V shape when it gets stabilized, and quantify other characteristics. So here are just some stills showing the exact same phenomenon for those propellants here. But we really wanted to understand, again, like, how does the surface evolve over time? How does, this middle burning layer of propellant compare to the burning rate of the same thing, but just not layered, essentially, right? So for example, this iron oxide layer, like, does that burn as fast as just a normal iron oxide propellant, like a single material propellant? And same for the nano aluminum. So we did some burning rate experiments to explore that. So typically for burning rate experiments, we put that on a log-log scale, and we do a curve fit to figure out essentially the slope of this and then the intercept. So usually we care mostly about the slope. In propellant land, we want to see, okay, is that slope reasonably stable or not? Usually we don't want it to be something like 1, but in general, the slope can kind of give us information about, are these two materials burning the same or similarly? So to kind of orient everyone on this, I have essentially on both curves. So on the left, we have data related to the iron oxide. So if it's L iron oxide composite propellant, that's the middle layer of this. And if it's no L, essentially that means that we're comparing the burning rate, the linear burning rate of just normal iron oxide propellant. And then we have APCP, which is just the linear burning rate of normal ammonium perchlorate propellant, right? The slower burning one. So, and then on this plot, we're looking, it's labeled similarly, but the additive is nano aluminum instead. So in general, we were comparing these. So this curve here is just of the normal slow burning propellant. And then we compare those two, we look at that iron oxide layer and the normal single iron oxide material. And we found that those burning rate slopes were pretty much the same. So if we compare those here, I have the N, and we look at, okay, the burning rate of that inner layer compared to the burning rate of that material by itself, pretty much the same. No real difference there. So that was good. However, when we look at this nano aluminum data, this curve is the same as this curve on that plot. So again, the slower burning layer. And then the black represents the burning rate of just nano aluminum based propellant. So no layers, just by itself. And then this lighter gray is the burning rate of this middle layer here. And what we found was this middle layer actually does burn slower than if you had the normal nano aluminum by itself. So you could see 0.44 versus 0.56. So the question was, why is this burning a little bit slower here at this middle part? Well, when it comes to aluminized propellants, a portion of the burning rate, so I think something like 10 to 15%, is attributed to radiation feedback to the surface. So essentially, it will burn about 10 to 15% faster because of that effect. So here, since we only have nano aluminum in like 1/3 of the surface, essentially, it's not getting as much radiative heat feedback as it would as if the whole surface was essentially full of nano aluminum propellant. So we do see some slight effect here, but in general, adding a small portion of either, some catalyst or some nano aluminum to a traditional, ammonium perchlorate propellant will improve the burning rate overall of the structure and will increase the burning surface area. And then kind of quickly, we did try to define some new metrics. So based on these high-speed image data, we did define something called surface length. So we're really trying to understand how is the surface evolving over time. We also measured the thickness of that middle layer, and then which is D, and then W would be the thickness of the entire strand. And based off of that, we also try to figure out, okay, how does this evolve over time? So we tried to say, okay, when something ignites, the surface length and the width are relatively flat. So that's close to 1. But over time, you can see that surface length will increase. But then at some point, it stabilizes, right? It doesn't really look like it's increasing anymore. So we try to quantify something called transition time. So transition from a flat surface, or S over W is 1, to where it does increase, but then it stabilizes again. So we kind of quantified that value, and we found that for the nanoaluminum, that transition time was relatively fast, or faster compared to the iron oxide. But in general, there are a lot more things to define in terms of this combustion. We're very used to just saying, okay, what's the linear burning rate, and looking at data that way. We're not really used to looking at what happens when you have a multi-material system. So we're definitely looking into understanding those dynamics more. Okay, so next thing we're working on is dissimilar material printing. So this is mostly focused on printing thermoplastic materials together and either something like a propellant or some sort of polymer-bound high particle mixture. So the goal of this work is to co-print these types of materials together. And there are a few reasons in my field why we want to do that, but there could be other applications outside of this. So we're trying to make our approach widely applicable here. But in our field, one of the applications is, so for example, that propellant grain I was talking about quite a while ago, typically it is supported by a liner around that propellant. So it's usually not very thick, it's relatively thin. And the purpose of that liner is to kind of protect the motor casing from the heat of the propellant. Typically you want to make sure that, when you're bonding this propellant to that liner, that there's no delamination between those two layers. Because if you have delamination, your propellant flame can spread, through the interface, which could kind of blow apart your propellant chunks and possibly your motor. So one advantage could we co-print the liner with the propellant grain as we go. So not only can we have more control potentially over the adhesion of that, but we can kind of monitor, okay, is this bonding or not? So that's one application. Another application is from a combustion standpoint. So we have the ability to make what are called reactive wires at Purdue. So essentially we can make a filament that can burn pretty fast. So those filaments can be made out of aluminum and PVDF, for example. And we have several papers on this at Purdue on how that is done. But essentially we've seen in the past that this can burn faster than the propellant around it. So the idea is that instead of trying to cast the central port here so that we can control how the propellant burns over time, what if we filled out the central area with like just this reactive wire or some other interesting structure, so that when we burn it, it can open up this burning surface area very quickly. So I have an example of what that looks like here. So here I have the wire and there's propellant around it. So I'm gonna play the video. And you'll see once the flame hits this wire, it very quickly opens up that burning surface area. So you can essentially have a fully dense propellant grain where the middle part actually contributes energetically compared to just air that doesn't contribute any energy. So obviously, if we wanted to make structures like that, we need to be able to understand the bonding between the two, potentially co-print the two, especially if we want more complex structures than just a simple line, essentially. So we're really trying to understand how do we integrate fused filament fabrication with either direct write or vibration assisted printing to enable this process. And we really want to understand how can we manipulate that interface between these two materials? So, you know, what kind of material matches will matter for this interface? Will the, you know, surface roughness from the 3D printing itself affect that interface? Do we need to consider adding copolymers or things to improve that? So in general, we're highly interested in like, how does this, you know, material, like we have a rigid thermoplastic bonded to something that's rubbery, right? We really want to understand like how those two materials bond together. So, and like I was saying, you know, energetics is not the only place this could be applicable. You know, if you're trying to 3D print, you know, maybe some flexible ink or something onto some other rigid kind of thermoplastic or backing, you know, you might want to understand like, okay, if it's bending, how's that debonding? So this is something we're trying to look to generalize. So recently I had a student present some preliminary work at AIAA SciTech conference in January, but essentially he was attempting to understand how we measure these two, the adhesion of these two dissimilar materials. So I will say we're not truly measuring adhesion in a classic material science way. We're really just looking at kind of what's that peak force for these two things to separate. So the approach we decided to use was to use essentially a modified double cantilever beam test. So double cantilever beam test is essentially when you have, you know, two things together and you're peeling them apart and they have relatively close matching bending stiffness. However, that wasn't necessarily the best approach for what we're trying to do, like the classic version, because we do have a rubbery material and a rigid material, but we did find someone who modified that. So essentially what they did was to make these two parts bend more equally, you can reinforce that weaker part with some stiff backing. So what we did essentially was we did some calculations. And what we did was we have something called a thermoplastic layer. So this is the actual part, one of the layers we want to peel apart. Then we have the HTBB on that other side of it. So again, this is something we want to peel apart and we want to look at that interface between the two. But we reinforce the HTBB with a thermoplastic backing. So essentially, we can see that that thermoplastic backing is not as thick as the thermoplastic layer. The only reason it's there is to reinforce the HTBB so we can bend the two parts away from each other more equally. So in practice, it looks something like this. So it's a bit messy because we have to improve our mold process. The HTBB kind of got everywhere, but here would be the thermoplastic layer. This would be the interface of the HTBB to that thermoplastic layer that's bending apart. And this would be the backing that's helping to reinforce the HTBB as we're splitting it apart. So when we made this, we had an initial crack that we had made with some tape, and then we're driving a wedge between the two. So again, the whole point of this was preliminary data. There's definitely improvements to be made with this setup, and we're looking into that. But to start off with, we wanted to see, okay, can we see some qualitative differences if we change the thermoplastic material? So for example, we used PLA, ABS, and PVDF, and then HTBB was kept the same. So here I have that test matrix, and there's many more tests to go. Excuse me, but we did change the material type, or pretty much a thermoplastic material type. We did change a few things like loading rate just to kind of get bearings on how this test was working. And then I have the load cell for reference. But in general, yeah, there is clearly a loading rate dependence, which is not unexpected. But in general, the key thing here is looking at least for the same loading rate and for the different materials, we're starting to see some quantitative differences here, or maybe more qualitative, I guess. But we're looking at that peak force when essentially those two are peeled apart. And that's the peak force of the wedge that's being measured. So we see, okay, we got somewhere in the 70 to 80 range here. This is more in the high 60s range, and this is much lower for the PVDF, which is what we were hoping to see because it's not going to bond as well. So here I have some representative curves of this test, and essentially what is happening is we're loading the wedge between those two layers, and then it's increasing until something starts occurring. So it either is debonding or maybe it's tearing or something like that. We still need to refine this process a bit to make sure we're looking at the right mode. But in general, we can see some differences here. So there are some improvements to be made. You know, we do see some multi-peak things, and we want to redesign this wedge interface a bit better, so it's not directly on this HVB and whatnot. And we're also considering maybe pulling them apart rather than driving a wedge. But in general, we can see some differences in that peak. So either here it's tearing or there's some slight differences. But here the PVF is definitely, from what we've seen in the sample, it's definitely peeling. So that means it's not that strong of an interface compared to these other materials. But in general, we do want to improve this process because we want to have a way to compare these materials together. And ideally, we would like to measure differences between, you know, like this 3D printed surface and HB and whatnot. And then finally, I'm almost done. I just want to give a quick teaser of the AFOSR project. But we're now also looking at how do we control the microstructure of plastic bonded explosives. So this is work that we are going to be doing, but I'm just going to kind of frame what we're trying to accomplish with this work. So when we're looking at a plastic bonded explosive, that's pretty similar to a solid composite propellant. So if you think way back when I had those slides where we had some particles and some smaller particles in a matrix, it's kind of similar to that, but a higher content of particles. But essentially, there could be defects that form within a plastic bonded explosive. So for example, there could be very tiny pores, or there could be a cracked crystal, or a crystal could debond from the polymer. And all of those defects will change the sensitivity of that explosive. So for example, there are these things called hotspots that can form if you, for example, detonate your explosive with impact, or if you vibrate your explosive. So hotspots are something that essentially they form in a certain type of defect. So it has to be a certain size or a certain type of defect. But essentially, it's kind of like a large increase of temperature that happens in a localized area. And it can make the explosive go off before it should, with less input energy than what it was designed for. So an example of that would be, actually I'll explain this one first. So this would be an example of what a current microstructure of a plastic bonded explosive would look like. So this is HMX with HBB. So we can have all these particles here, like that's the lighter gray. And then the darker gray would be examples of binder-rich regions. And then we can see that it's really small, but there's some black patches there, which could be defects, right, of pores. So in general, like how these pores are formed, or how their binder-rich regions are not, or how these particles are pressed against each other, will affect where hotspots localize. So over here, for example, I have some plots of where people put together 3 crystals. They either put them like touching each other or separated, or maybe they debonded the crystal from a polymer or whatnot. But in general, here they're vibrating the crystals to see where these hotspots localize. So for example, we can see some regions where the temperature is localized and increasing. So that'd be an example of like a hotspot forming, and it's going to really depend on the microstructure. So what we're looking at now is, can we change the way we arrange this microstructure to make it more consistent, so we can better predict when these explosives will or what they're sensitive to. So for example, you know, like maybe we could preferentially you know, get rid of certain size pores, like pores that are known to cause hotspots, or maybe we want those pores. Maybe we want to engineer some other type of features in here. But in general, the goal is to improve the consistency of these plastic bonded explosives. So this is work that we're looking at, primarily using advanced manufacturing techniques to figure out how do we lay all these pieces together to make it perform more consistently, and how to make it safer. Because if it goes off with too little energy, or less energy than you expect, that would really not be a good thing. So this is work we're currently going to start on. So with that, I'm going to conclude. So we've used vibration assisted printing to make very viscous print this mixtures into different shapes without modifying our propellant. So we didn't have to use solvents or other things that were different than a traditional solid propellant mixture. We're looking currently into how can we find either photopolymers that are compatible with energetics, or maybe some dual cure system that are compatible with energetics that provide us reasonable mechanical properties, but allow us to print taller, more complex structures. We have explored multi-material 3D printing. So part of that is, we either change the propellant mixture, or we look at dissimilar material printing to understand, the adhesion of these materials. And then we're now starting to look into controlling the microstructure of plastic bond explosives. But in general, our work is to understand how we can advance additive manufacturing science to actually 3D print these energetics and control the structure better. So with that, I'd like to thank all of the students who have contributed to this work and my collaborators at various locations. Thank you, Bruno, for inviting me here, and for other coordinators of the seminar series. And this research has been funded by various agencies like NASA, NDSEG, and AFOSR. So thank you very much.
All right, Monique. Thank you very much. One of the things that Zoom is not very good at is a clapping. Hopefully you imagine the warmth of our community, everyone pretty excited about your work. So I'll kick off our Q&A, and everyone in the room, please just type, let me know if you have questions, and you can unmute yourself to ask questions to Monique. So why don't we get started with Natalia? You can unmute yourself and ask the question.
Excellent talk, Monique. I enjoyed that a lot. And I do have a few questions, but I'm going to start with that. I saw you when you were talking about the different binders that you could have for the propellants. And you mentioned that, with one you would have more porosity and the other one you wouldn't. And you were also comparing the 3D printed parts and the casted ones. I didn't take notes of the exact number of the slide, but that's what I had in mind. So my question would be, you said that you were looking into the one that had less porosity because that would control better the rate, the burning rate, right? But could the porosity be beneficial in terms of like increasing the surface area and then increasing the burning rate? Or is that just a matter of controlling, or is porosity actually a really bad thing for propellants?
Yeah, that's an excellent question. So in general, yes, porosity will affect how it burns. So it will in general increase the burning rate. The problem, I would say, is if you have too much interconnected porosity, because then that can kind of propagate down and cause propellant to split apart, or like chunks to split off and delaminate and whatnot. So some porosity is not necessarily a bad thing, but in general, we can really understand how it burns better if it's a fully dense type of material. So in general, with energetics, we try to achieve as full density as possible because those are properties we can predict better. But yes, some porosity will affect how it burns, and some porosity is not necessarily the worst thing to happen. It just needs to be in a reasonable amount.
I see. Thank you.
I had a question, Monique. Can you take us back to the slide where you had the wire and the composite around the reactive wire? Can you play the video again for us one more time?
Oh, yes. Play.
What is the wire material here?
Yeah, so this is aluminum particles in PVDF. So we have a process to make those custom filaments here at Purdue with a typical like Philibot extruder. And yeah, you can 3D print those into structures on an FFF machine. Okay.
And so this is the core wire. There is aluminum mixed with an oxidizer already.
Yeah, exactly. So yeah, so far we've just kind of cast those into propellants. So there's an excellent paper from my colleague, Dr. Diane Collard, who used X-ray imaging to see like, okay, if we have more complex 3D printed shapes cast in a propellant, how will it burn? But at the same time, you can't always long term, you're not really going to be casting propellant around these wires. You're probably going to want to co-print them to understand like the adhesion better, or to process more complex shapes.
So none of the structures that you've printed so far are structural components to carry payloads. They're geometrical burning surfaces, but there's no structural component at the moment.
Typically not. I will say though, for the wire itself, there was a separate series of papers written by Dr. Trevor Fleck. And one of them was like, what if you could print this aluminum PVDF material into something more structural, and then have it be consumable? So he did write a paper related to that. So I think he looked perhaps more at those structural properties, but in my work, we focus more on how do these structures affect the combustion overall. But we still want to have some basic understanding of mechanical properties, because if your motor like tips over or something, we don't want things just breaking, whether it's a photopolymer or bonding if it's a system like this.
And as you look into the similar material printing, your focus, do you see a focus to integrate a little bit more with metal 3D printing?
Yeah, that's a good question. Right now I'm pretty open to different applications, because I'm really, even though we have our own like target application here in energetics, I'm really interested in like, how can we make more generalizable like test methods? How can we make more generalizable relationships here? So I'm not necessarily like, oh, it has to just apply to energetics, because I know there are other people printing other materials together and they're like, oh, we made this, but I don't know if they've necessarily quantified like those bonding properties. So in general, if there are other applications that are relevant here, then that could be of interest.
All right. And one more question is, how do you ignite these systems? And what are the different types or possibilities for ignition circuitry, or using lasers or impact? What are the possibilities for igniting this system?
Yes, so for a composite solid propellant, you could either use resistive heating in a nichrome wire, so it just gets hot enough and then it ignites the propellant. It's not always the most consistent method. If it's a larger system like a motor, you could use some sort of torch system, or some pyrotechnic system that burns and then kind of ignites it. There are people who have done laser ignition of propellants, so that is a possibility as well. And then in terms of like plastic bonded explosives, that's entirely different type of ignition, because it kind of needs like easier to ignite explosive to then ignite the actual explosive in a sense. It's sometimes difficult to directly ignite it. So it kind of needs some assisted ignition there. So, but in general, there are several different methods to ignite these types of energetic materials. It just really depends on the system you're working with.
All right, I have one more question. If we have, feel free to let me know if you have a question, but I'll keep firing questions because I'm super excited. One more question I have is, what is the trade-off? It's sort of the performance metric of your burning rates, or whatever the metric you care about, relative to the nano aluminum size. Do you, like, if instead of, let's say, 3 nanometer particles, you had 10 nanometer particles or 20 nanometer particles, what is the sort of trade-offs there that you would get?
Yeah, so in general, there is a trade-off, and there's a trade-off in the particle size of aluminum in a lot of energetics, is specifically propellant. So I believe the common convention is like below, I think it's 10 micron. And below 10 micron, it is, I think, kinetically controlled combustion versus Above that, it is diffusion controlled combustion. So there definitely is some sort of trade-off between particle sizes in a sense and how the material burns. So like that could correlate to the slope of the burning rate curve, for example. And some of these effects can also happen with other types of materials, maybe not exactly kind of the same like kinetic or diffusion control, but in general, like there are critical particle sizes that do affect kind of overall behavior of how propellants burn.
What is the current particle size that you're working?
Yeah, so for the nano aluminum, I think it was 70 nanometers or 90, but I think it's 70.
Okay.
I did write that detail in the paper, but yeah, there's yeah, and in terms of like the ammonium perchlorate particles, I've worked with 60, 130 micron ammonium perchlorate, although if you measure it, it's actually a little larger than that. It's more like the D50 is like 170 micron, I think. But and then we have smaller ammonium perchlorate particles, which are about 20 micron. And the reason we chose this size is because of the diameter of the nozzle we're printing out of. So it'd be challenging to print like 200 micron particle diameter out of, or larger than that, like 300 micron out of a nozzle that's, you know, within the 400 to 600 micron range or diameter range. So as long as your nozzle is big enough, you should be able to handle different types of materials. But in general, our energetics are kind of large. So I know like other people can get good solids loading if they use nanoparticles, but for us, we're kind of constrained by these AP particle sizes or explosive particle sizes, which tend to be larger.
Thank you. Adnan, go ahead.
Thank you, Professor McClain. A very excellent talk. I have a question as regards your vibration-assisted direct ink writing process. My question is more regards the stability. So I recall you saying you require structures that have, you know, superior surface areas. One way to have that is by, you know, printing more intricate structures, for example, honeycombs. And so if you are applying vibration at the tip of your nozzle, how stable is the process in terms of upscaling to be able to print more intricate structures that could, you know, allow for advanced surface areas?
Yeah. So the vibrations, so since these mixtures are more viscous, we haven't really noticed serious, like for example, wiggling patterns in our prints. So in that sense, you know, it's a little, I guess, more stable. But if it was more inky, that would probably not be the case, right? You probably see this kind of thing happening. So kind of that mixture really matters in terms of vibration assisted printing. But in terms of printing those more complex structures, I think in general, like our process, there's another paper kind of comparing direct write of clay to vibration assisted printing, and there are pros and cons between both, but we can get kind of finer features with this vibration assisted printing, but kind of the main challenge we face in terms of like getting more intricate features, I think, in a propellant is, you know, we have to be able to lock that shape into place. So I'd actually say at this point, I think we're more constrained by our binder system than the printing process. But in general, yes, like if you're scaling this up to print larger structures, you want to make sure that flow is consistent. You may not need this fine resolution everywhere. So you may not need to print everything with vibration assisted printing. Maybe more direct write based systems would be fine if you're printing like larger structures and you want finer features in one place. You know, that's where you use this process. So did I answer your question?
Yes, you did. I think a follow-up would be, these are explosive materials essentially that you're printing. What is your drying process like? Because yes, what is your drying process like essentially?
So we use, so we receive the materials like ammonium perchlorate and whatnot from different vendors, but in general, we can dry them like in an oven or something beforehand, as long as they cool down. And then other than that, we don't necessarily dry our propellants afterward, but yes, like you know, as I mentioned, like early on, humidity is a really important factor in terms of the performance and safety of energetic materials. So it's not necessarily like ideal to leave them out in a super humid environment. But as of now, what we do is we kind of pre-process that ammonium perchlorate, especially if it's in the summertime where it's more humid here. And then we also try to keep our polymer stored in a reasonable environment, and, you know, limit the shelf life. So we're not putting humid infused polymers into these systems.
So you technically print in a clean room essentially to avoid external factors affecting your print?
It's not necessarily a clean room. It's just kind of like normal chemical lab setting. Yeah.
Thank you, Professor.
All right, we have time for one last question, and we can do your question, Natalia.
Yay. I was curious too. I'm not sure if I can formulate that question right, but as you talked about the propellant shoe being directly influenced by the pressure in the chamber, inside the chamber, in the very beginning of your talk.
Yeah.
Right. So all of the 3D printed structures that you did, they're mostly ignited like in a normal atmospheric pressure, right? So how would the chamber design be related to the complexity and work to, you know, 3D print these very specific designs for propellants, but would the chamber be the same? Like, is that in the future work somehow? That affect
Yeah.
a lot?
Yeah, I think I understand your question. But essentially, yeah, so it kind of depends on the solid rocket motor you're talking about, but in general, like the shape of the motor is typically cylindrical. So the idea here is like within that cylindrical boundary of like the hardware, we want to have the freedom to make the different structures we need, because essentially that initial structure affects, like as it burns, it affects the pressurization rate inside that cylindrical area. So in general, we're trying to focus on changing that geometry rather than trying to change like the hardware itself. But in general, like as your pressure increases, your propellants tend to burn faster. So it's kind of like a feedback process. Like as it's the propellant's consuming, it's pressurizing the chamber, the higher pressure makes the propellant consume faster. The burning surface area, like as that increases, it makes it consume faster too. So in general, like all those factors kind of play into like the actual design of the motor. But there are some motors that could have a less cylindrical shape, I guess, structurally. There's some diagrams that like NASA has where it looks more kind of like oblongish, I guess. But in general, like that hardware shape will be fixed, and then you change change out the propellant inside.
I see.
So hopefully I answered that properly.
Yeah. That was very helpful. Thank you.
Okay, cool.
All right, it's exciting to be able to catch up to your latest work, Monique. Thanks for sharing. On behalf of the committee, thank you, and I wish everyone a good afternoon. Any last words, Monique?
Thank you so much. I enjoyed getting to share this work with you. Yeah, until next time.
All right.